which is basically chapter number 9 of your book. So if you remember from the last lecture that we were discussing about the drag force. So as we discussed in the last class, that the drag force is the force which the flow experiences when in the flow direction parallel to the flow, right? When it flows over a solid body, right? So it has got two components. So one component is, if I kind of recap it, one component is friction drag. That is due to the friction between solid surface and flow, and it depends upon the viscosity of the fluid as well as the du or dy at the solid surface, right? Because we all know that that bond shear stress is mu into du over dy, right? So this is one component which is friction drag, and it is usually it is significant when we have got streamlined bodies. Streamlined bodies. So streamlined bodies, what are the examples? They are kind of a flat plate which is placed parallel to the flow or the aerofoil. So it means the surface area parallel to the flow is more, and the frontal area on which the flow is impacting, striking, that is less. So that is kind of streamlined body. So let me write it here. So streamlined body, when the ratio of frontal area to the surface area is less or low. It means that if we have got a thin body like this, in which the surface area is this one total, and frontal, this is frontal area. If the flow is coming from here, this is frontal area, and the surface area is this one, bottom and top surface included. Right? So frontal area is low, and the surface area, which is this one, that is quite huge. Right? And then we have got a second type of drag, which is pressure drag. So we also call it foam drag. So this component of drag is usually where we have got a blunt body. Blunt body means that if we have got the frontal area more, and so if the flow is coming from here, so this is kind of a blunt body, right? Because the frontal area is more, and this is frontal area, which is perpendicular to the flow, and parallel to the flow is the surface area, right? So in this case, the ratio of frontal area to the surface area is more, right? So that is a blunt body, and due to that flow, some kind of flow separation occurs on the back end. So this is the region where we have got flow separation region. So
सर ये समझ नहीं आई ये.
Yes, please ask.
सर ये frontal area greater than surface area, ये सर इसकी समझ नहीं आई.
A little bit on the first point. Here, if you look at this flat plate, right?
Yes,
base,
sir.
can you see this figure? What is the frontal area? Let me show you. This is this one. This is the frontal area. It means which is perpendicular to the flow, right? So you can see that
Yes,
frontal area is this one. What is the surface area here? So let me highlight it with blue. This is the surface area of the top and bottom surface. So can you see that frontal area is low in this case and surface area is more?
Okay, sir, समझ आ गई, सब समझ आ
Okay,
गई.
now if I go towards the second figure here, what is the frontal area of the base here? If I show it with red, you can see that this is frontal area here. Quite big frontal area which is perpendicular to the flow. And what is the surface area here? It is this one, the blue one. So you can see that the blue area is quite less, which is surface area, and the red area, which is perpendicular to the flow, that is frontal area. Right? So in blunt bodies, the frontal area is more and the surface area is less. So it means that streamlines divert and the flow separates. Now, what is the consequence of this flow separation behind that body, blood body? Here we have got, at the front, we have got here somewhere stagnation pressure, which is the maximum pressure. And here we have got, because of the flow separation, we have got low pressure, right? So now you can easily see that there would be a force in the positive x direction. The pressure at the front side is more, and at the back, yes.
सर ये जो फिश लाइक ओवरऑल स्ट्रक्चर शो हो रहा है सर ये फ्लो का सर वो क्या कहते हैं
ये streamlines हैं. Okay, thank you very much for your these are the streamlines, right? These are the streamlines which are flow is coming from here, right? So this is fish like which you are saying, that is basically showing this is the blood body, and here the this kind of divergence, it is due to the presence of this body. So these are the streamlines, right? Do you understand this?
Yes, sir.
Okay. So I'm sure that now you are familiar with pressure drag. So pressure drag would be there when we have got blunt bodies and the flow resistance number is more. And so this is a blunt body, and this let me. This circular cylinder or sphere, we call it usually semi-blunt body, right? So in this we have got surface area as well as the frontal area, so we call it semi-blunt body. So that is basically cylinder or sphere, right? So up to now we have discussed two components of drag. One is friction drag. So as I have told you that friction drag would be more when we have got streamlined bodies in which the frontal area is less and the surface area is more. And pressure drag would be more in the case when we have got higher frontal area and the surface area is less, so that there would be flow separation at the back end. So on the front we have got high pressure, and on the back side we have got low pressure. So that pressure difference gives rise to a force in the positive x direction, which this player would experience, right? Would experience. So these are the two components, and then we discussed the detail in the last class that friction drag, as I have told you, that it is a strong function of the viscosity and velocity gradient at the solid surface, and then coefficient of drag due to friction, that would be equal to frictional drag force divided by half rho u squared into area. And then we also discussed about the pressure drag in the last class. So, and the total drag on a body is the summation of drag force due to friction and the drag force due to pressure difference, right? So after that we discuss that how this drag component changes for a semi-blunt body like a sphere or cylinder or like this, because L upon D, if it is L upon D, L is the because length and D is the diameter. So diameter D, capital D, tells you about the frontal area, and this length tells you about the surface area. So when L upon D ratio is very less, it means that we are talking about a blunt body. So in blunt body, you can see that the drag coefficient is very high, right? You can see in the figure that if we have got a very thin plate placed perpendicular to the flow, the CD value is around approximately around 2, right? So, but when we increase the length, then it means that we are making a streamlined body. So it means that the coefficient of drag reduces. So it means that generally we know that if the body is thin, then the drag force on that would be less. So that's why aerofoil shape is kind of a streamlined body type profile. Or for that sake, if we talk about Formula One racing, so we want to make the Formula One car race the frontal area very low, and it should be a little bit streamlined structure, so that we have got less drag force on the Formula One car. So then in the I have discussed that for these two bodies the drag force is equal. So it is very surprising to see that even this length is 10 diameter, and here we have got a cylinder which has got a diameter of D, and you can see that these two objects have the same drag force, but the CD value is, if you see circular cylinder, CD is 1.2, and for this here the CD value is 0.12. CD value for the aerofoil is very low, but because the overall surface area is more, the drag force would be equal to that, right? So it means that if we can make a body streamlined, which means that if we can increase the length and reduce the frontal area, it would make the drag force less and less, right? So I hope that this point is clear to you. So I am just repeating it, that for because it is very important point in terms of design of bodies when they are going to be exposed to be in external flow situation. So the last slide which I shown in the last week's lecture, that was this, that here in the, okay, let us discuss this maybe on the whiteboard as well, so it would be better. So let me copy it here. So first of all, if we see this figure, okay, so I'm going to copy it and paste it here. Okay, so what is this? Basically, this is the flow around a flat plate which is placed perpendicular to the flow. So basically, this is the plate. Oh, sorry. So this is plate, which is, and flow is coming from this side. And this divergence of streamlines are shown, and then here we have got Reynolds number is 10 to the power 5, which is basically 1 lakh. So you can easily see that the flow would separate from these edges, and there would be some low pressure region here. Now here on the right hand side, they have shown two areas. One is, if I kind of tell you that what are these two areas, one is shaded region, that is the friction drag, and one is blank region. So that is due to pressure drag. So now here you can see that the because the flow would be attached at very less surface area, because the surface area available for the attachment is this, right? So because that surface area is very low, so you can see that the contribution of the drag force due to friction, that is very less. That is only this bit, maybe, which is like 5% of the total drag. And then the rest of the 95% of the drag, that is due to pressure drag, because the flow would be separated. So the frontal area is more, so that's why the pressure difference would be higher. And because we know that the drag force due to pressure, that is CDP into half rho u square into area. And this area is the frontal area here. Please remember, this is the frontal area. So because the frontal area is more, let me show it by the blue line. So this is frontal area. So frontal area is more, so that's why 95% of the drag is due to pressure drag. Now let's see the next figure, which we can try to do it here again. So now we talk about flow over circular cylinder. So let me copy it. So I copy it, and now we put it here. Okay. Now, this is the second figure, which is semi-blunt body. So we are not talking about semi-blunt body. Reynolds number is same, but we have got semi-blunt body, which is circular cylinder or sphere in this case. So now you can see that the total magnitude of the drag is less for the semi-blunt body. Because that is the thing we have learned, that when we try to make it more streamlined, then the total drag force would be less. Now you can see that the friction drag, which is the shaded region, that is almost the same as that of blunt body, right? Because the surface area is not very significantly increased, but the total this pressure drag, that is a little bit less. Pressure drag component is, let me show you. This is the pressure drag component, the green area in both figures. So these are the pressure drags. pressure drag. And this shaded region is due to friction drag, and you can easily see that the close wake region, why it is less, because here the wake region was, let me show, wake region was this one, very big. But in this case, the thickness of the wake region is a little bit less. So when the wake region or the flow separation region is thickness is a little bit less, so pressure drag component would be a little bit less, right? Now, if we move on to the next one, now we have made it more streamlined, which is kind of an aerofoil shape. Copy it again here. Now I am going to copy two things here. One is here. Okay. So now the above figure, which is shaded here, that is the flow over a streamline kind of body, which is aerofoil in this case. So in that you can easily see one very interesting thing, that the total drag, which is shown on the right hand side, that the magnitude of the drag force is very less as compared to the flow over cylinder or a flow over flat blade. The reason for that is that we have decreased the pressure drag component significantly. But you can see from the comparison that the shaded region, which is shown by this rounded line, that is increased. So it means that the friction drag is more. Friction drag more. Why it is more? Because the surface area is more in this case. You can see that this is the surface area on the lower and upper side. But because this frontal area is now less. Now the frontal area, which is this one, this is the frontal area. Now this is less, and then the second thing, the wake region, which is behind the cylinder, that is almost negligible. So it means that the pressure drag is very less. So we have increased the friction drag by a little bit, but pressure drag has been significantly reduced. So it means that 90% of the drag was due to pressure drag. So we have we have decreased it by making the body streamlined, and in the process we have increased the friction drag a little bit. But that doesn't count so much. So that's why the total drag is reduced, like maybe 5 times or maybe 10 times as compared to the semi-float body like cylinder or sphere. Now the second interesting thing which I wanted to show, now the figure which is on the bottom, that is the circular cylinder here, which is this, and it has got diameter which is 10 times less than this total height, right? So one thing is very interesting, that the drag force on these two objects, they are equal, right? Drag force is equal, so it means that this small cylinder would experience the same force as this bigger body, and even this cylinder is very small. But because this is a semi-blunt body, so the pressure drag would be higher, because you can see that here this is the wave region, so it is quite big. It is comparable with this, so that's why the magnitude of drag force, which is shown on the right hand side, it is written as the same total drag. So you can very note it very interesting factor, that these two bodies, which is 1 by 10 of this kind of, they have got the same drag force. So so it means that if we can make the bodies more streamlined, then we would have a very favorable results in terms of drag force. So that was the major crux which I wanted to tell. And then you can see that if we make it like Reynolds number 10 to the power 7 in the bottom figure, you can easily see that which is 10 million. Now the drag force is very higher, because the pressure drag is also very high here in the last figure, which is 10 million, 10 to the power 7, if I can kind of make it a little bit. This one, you can see 10 to the power 7. So because now the wake region is more, so we have got. So the major design constraint here is how to make this wake region low and less and less. If we can make it less, then we would be able to achieve lower drag on the body. And then when there is lower drag force on the body, it means that we would be requiring less fuel for that vehicle or that aeroplane to move in air. So that is the major design constraint, that how to make that vague region which is behind, which is the region behind the body where the flow separation occurs, how to make it less and less. Reason for that we want to make drag force quite less. So now I hope that I have given like 10 to 15 minutes extra in this class just to emphasize this point. So I hope that you kind of now you get the crux of these two components of drag, which are friction drag and pressure drag. Okay. So now in the last class we are going to apply these.
सर
yes.
ये जो आखिरी बॉडी में सर प्रेशर ड्रैग है ये ज्यादा है पहले वाली शीट के मुकाबले में, तो ये इसी वजह से है कि इसका रेनॉल्ड नंबर ज्यादा है.
Very good. Excellent. Excellent. What is your name?
तबरेज सर.
Tabriz, yes, very excellent point. Because while that, if I write the formula for the drag force here, that was CD into half rho U square into area, right? So area is kind of same. If you see the figures, the frontal area here, it is the same as the diameter of this. Rho would be the same. CD value, that would be kind of same magnitude. The only difference which is making, which is very applicable, which is quite dominant, that is U scale, right? So that is the Reynolds number effect. Because Reynolds number is, if you remember from your FM1, Reynolds number is rho U d upon viscosity. So that is excellent point. So the base, that is very good. So that was a good point indeed. That Reynolds number is high, so that's why this. So after that, now we are going to apply this knowledge to the flow over cylinder and sphere for different Reynolds number. Flow over flow for cylinder and sphere. Right. So as Kabir has pointed out, that the drag force and drag force, which is total drag and CT value, they are function of Reynolds number. So it means that the coefficient of drag and total drag force would depend upon the flow velocity. So we are going to discuss different flow scenario for different Reynolds number for flow over cylinder. So let me take you through those different flow scenarios. So first of all, I am going to copy the first figure here. So now the flow is going from left to right. So here, let me copy it. So this is the figure A. So this figure shows that we have got Reynolds number. Sorry. Okay, so this figure is for the Reynolds number which is less than 1. So it means that this is kind of very creeping. We call it creeping flow. So it means that flow velocity is very less. So when the flow velocity is less, the flow tends to stick with the cylinder surface. When the flow is going to stick with the cylinder surface, so it means that there is no flow separation at the back end. So it means that I can write no flow separation at the back end. Right? When there is no flow separation, it means that there is no pressure difference or minimal pressure difference between front and back, because the major pressure difference arises when there is a kind of flow separation. So it means that when the Reynolds number is less than 1, the total drag force on this scenario, that is predominantly due to friction drag. Friction drag is due to the wall shear stress at the cylinder surface. So because the surface area available for that friction drag is maximum because the flow is sticking with the cylinder surface. So friction drag would be higher. Pressure drag is minimal. Right. So this was the case when we have got deeping flow. Now, if we increase the Reynolds number, like for instance, if we make Reynolds number is equal to 10, so it means that now we have made the velocity more. In that case, we would have some kind of flow separation. So let me copy it again here. So this is the figure B. So now if I copy it here, now you can see that in this case, Reynolds number was equal to 10 or 10 to 20. So when Reynolds number is 10, you can easily see that there is some kind of flow separation at the back end. So that is shown by this area. So these two vortices, we call them standing vortices, standing or stationary. So by stationary, it means that they are not going to move along with the flow. So they would be present all the time in the back region, and this is kind of steady flow. So it means that flow pattern would remain same. And now in this case, because there is a flow separation, so friction drag would be becoming less and less as we increase the Reynolds number. Friction drag would become less and pressure drag would increase. At this Reynolds number, we can say that 50% is due to friction drag and 50% is due to pressure drag. While for the previous figure, when we have got creeping flow, we can say that 90% drag was due to friction drag and 10% was due to pressure drag. Now, if we move on to next case, then the Reynolds number is around 50. Now this is third case. Let me kind of copy it and then I would explain it. Okay, so now if we increase the Reynolds number in the range of kind of 50 to 100, so you can see those standing vortices which were standing there or stationary vortices, they are going to move with the flow. So you can see the pattern that those vortices they are moving, down the flow, and we call it Von-Karman. Okay, it is written here, oscillating Von-Karman vortex street wave region. So they would be actually moving along the flow. So we can always see the visualization of this kind of flow characteristics. So that's why I have selected a video which I have seen from the YouTube. So it would be a good idea to show you a video. So here you can see that we have got flow is coming from the left to right, and we have placed a cylinder in the flow, and we have simulated the flow at different Reynolds number. Like here it is 25, then 50, then 100, then 220. So basically we are increasing the flow velocity to increase the Reynolds number. Now please see that how the wave region would evolve at different flow conditions, at different flow Reynolds number. So you can see standing vortices in case of 25. When the Reynolds number is 25, you can see a standing vortex which is not moving here. But for the Reynolds number 50, 100 and 220, you can see that Von-Karman shedding speed. So shedding means that the vortex are being shed on the downstream and then they move along the flow in the downstream region. And you can see that once the vortex is shedding from the top side and then alternatively from the bottom side. So it means that there would be some kind of vibration in this cylinder, right? So we also use this for the energy harvesting. This vibration of this cylinder due to this von Karman shedding, you can see a very nice pattern of vortices which are moving downstream, right? So we call it von Karman shedding sheet. So let me again show it for you. You can see for the Reynolds number 25, there is no kind of motion downstream for the vortices, but for the 50 to 220, so they are kind of unsteady flow now, right? 50 to 220. So this is the von Karman. So it always occurs in cylinder. Then it also occurs in any cube or any plate which is placed perpendicular to the plate where the frontal area is more. So that is the characteristic of external flow, von Karman shedding state. So I hope that you can understand something from this animation. Which of course they have made it from the Fluent or ANSYS software. You can easily do it. Maybe it won't take more than a day to do this simulation to observe this phenomena. So I hope that you have learned some bit of that in your project. Okay. So that was something which we discussed the figure here, and then the next one is figure D and E, which is I'm going to show it here. Okay. So there we have got this one. Now, if we increase the Reynolds number beyond like Reynolds number, we are talking about range in fluid value. So maybe if Reynolds number is if for this case Reynolds number is it is around 10,000, and here we can say Reynolds number is 10 to power 6, 1 million. So
ये रैंडम नंबर सर किसकी प्रॉपर्टी है, फ्लोट की कि ऑब्जेक्ट की?
okay, excellent question. Who is this?
सर
Umair Khalid. Okay, excellent question. So let us see that if we write the formula for that, rho V d upon mu. Can you see any fluid property there, Umair?
डेंसिटी और विस्कोसिटी.
Yes. So it is density and viscosity. They are fluid properties. Right. We write it. Okay. What about velocity?
सर वेलोसिटी तो वेरी करेगी फ्लोट की.
So velocity is the flow property, right, Umair? It depends
Yes,
on the flow velocity. Okay. What about diameter? Diameter depends on the geometry of the object we are talking about, right? So it means
Yes.
that Reynolds number depends upon the fluid as well as flow and as well as geometry on which the flow is happening. Like for the, if you remember that for the internal flows, that when we talk about internal flows like pipe flows, Reynolds number was defined like rho u infinity into length of the plate divided by viscosity. So we are talking about this length here. Oh, my drawing is not the best, but okay, this is the length, right? So in this case, critical Reynolds number was equal to no, it is not the external flow. What am I talking about? This is not right. If we talk about internal flow, it should be I just wrote this formula for the external flow. Okay, so let me. For the internal flow, if you remember that we kind of defined it by rho into V d upon mu, and then diameter is the diameter of the pipe. So this is the diameter of the pipe. And in this case, critical Reynolds number was almost equal to 2100. After that, the flow would transition to turbulence. Now, when we talk about external flows, external flow like there are two examples I am going to discuss. That is, one is flow over flat plate. So that is something like this. So this is the flat plate and velocity. If free stream velocity is coming from here, u infinity here. This v is the mean velocity as we discussed in chapter number 8. So free stream velocity is coming here, and then this is the length of the plate, right? So in this case, Reynolds number is defined like rho into u infinity into length of the plate divided by mu, right? And critical Reynolds number in this case is like 5 into 10 to the power 5, half million. So it all depends on the geometry type of flow, that whether we are talking about internal flow and external flow, and then the second type of flow for the external flow, we can say that is which we are discussing right now, that is flow over circular cylinder or sphere. That is something like this, that flow is coming from here and going on top of this, right? So this kind of this. For this case, if we want to define Reynolds number, because this is external flow, so in this case, Reynolds number would be defined rho into u infinity. U infinity is the free stream velocity, 5 meter per second, 10 meter per second, which is coming in the fast stream, and then diameter divided by mu. And believe me, here the critical Reynolds number is around 2 lakh. So it all depends upon the type of flow we are talking about, right? Geometry and type of flow. So I hope that I have answered you to that.
Yes, sir.
Okay. So now going back to the discussion which we just slightly diverted, but it is for the good cause that you understand these things, because these are more important than doing the numerical problems. So understanding the nature of the type of flow. So in this case, we are going to put it here. Okay, so I'm going to put it again here. So, okay, that figure was also I have pasted here, but let us do it again. So in this case, as I mentioned before, that for the laminar boundary layer, because for the turbulent boundary layer, as I have told you, that the critical value is 2 lakh. So if we say that here Reynolds number is like what do you call it, 5 into 10 to the power 4, which is 50,000, so it would be laminar. And then here the flow Reynolds number is like okay, again if I say that it is 50,000, right, the same Reynolds number, but it is turbulent. Can we make can we make a flow over a flat board over a cylinder turbulent at this Reynolds number? Because critical Reynolds number is given to be 2 lakh. Is there a way we can make it math, or for that sake,
Yes, sir.
anyone? How can we make it turbulent at this 50,000? Can you think of any way that we can make it turbulent? Anyone?
Velocity of
No,
flow.
velocity is not going to change, because velocity is 50,000 here for both cases. So is it possible that the flow would become turbulent for the right hand side figure at the same Reynolds number, which is 50,000? Just think. Because flow
Geometry change करें.
नहीं, ज्योमेट्री भी चेंज नहीं करनी, ज्योमेट्री भी यही है, ज्योमेट्री के
फ्लूइड
ऊपर
चेंज करके
नहीं, फ्लूइड भी चेंज नहीं करना, फ्लूइड भी वही है, हर चीज वही है, सिर्फ एक चीज आपने सरफेस रफनेस. If we make this surface rough here, kind of roughness elements, if it is smooth, then the critical Reynolds number is 2 into 10 to the power 5, which is 2 lakh. But if this sphere, it is kind of rough on its surface, then there is a high possibility that the flow would become turbulent at low Reynolds number, because roughness would kind of trigger the turbulent transition before this value of 2 lakh. So that is the reason we put dimples on the golf ball. Have you seen ever a golf ball? You can see a dimple on that. Why we put dimples on the golf ball? Because that is not an aesthetic value. Because putting some dimple, it doesn't look good. So there must be a good reason for that, right? So dimples are put because we want to reduce this vague region. Because now let me explain it on a figure. Let me draw it here, and then I would explain 2, 3 very interesting phenomena. Okay, so this is kind of cylinder, so that is good. So this was center, So if we measure the angle from here in the clockwise direction, this is we call it theta. So usually when the flow comes here, if the boundary layer is laminar on the surface of the cylinder, then the flow would kind of separate from theta is equal to 80 degree. 80 means that at this location, this is the flow separation point. Flow would kind of separation point. Separation when we have got laminar flow, right? And when we have got laminar flow, you can see the wake region is quite big. This is the wake region where the flow velocity is different from the free stream velocity. Now, what if we can introduce some dimples here on the surface of the cylinder or sphere we are talking about? What it would do that it would kind of trigger it towards the turbulence at even the low Reynolds number of 50,000, right? So in that case, because we know that when there is a turbulence, we have got velocity fluctuation. Velocity fluctuation. Then due to that velocity fluctuation, the flow would remain attached up to this point, which is theta is equal to 140 degree. So it means that it would remain also attached up to this point on the downside as well, right? And the wake region would be low, right? Now you can see for the laminar region, because the flow separated at theta is equal to 80 degree, and for the turbulent flow it remains attached. Why it remains attached? Because we have got wall normal, or in y direction wall normal, y direction velocity fluctuation. V velocity. U is the streamline velocity. V is the wall normal velocity. If we say that this is x and y, x, y. So V is the velocity in the y direction and U is the velocity in the x direction. So we have got flow separation, velocity fluctuation. So it keeps the flow attached up to theta is equal to 140 degree. So we have got less wake region. When the wake region is less, so the total drag force on that object would be less. So when the drag force would be less, then that golf ball would travel more into the space, more distance into the space, right? So that is the purpose, only purpose that we put dimples on the golf ball surface. So now we can explain another phenomenon from this figure. That is the phenomenon of reverse swing in cricket ball. Reverse swing. In reverse swing, if you remember that one side of the ball is kept shiny, like this, if I kind of remove it from there. So in that case, one side which is the top surface in this case, we make it shiny. So what will happen that the flow boundary layer would separate at theta is equal to 80 degree at the top surface, but the boundary and we make it rough on one side, or we keep it like as it is. So in that case, when the ball would be delivered, then on top surface there would be a vacuum here, because the boundary layer has been separated, but the flow would remain attached here. So it means that we have got a positive bi-direction force. So it means that the ball would travel towards the shiny side. So that's why the bowler usually hide the ball, that the batsman cannot see that where is the shiny side until the ball is delivered. So that he cannot detect any reverse swing which is going to happen when the ball is delivered by the bowler. So that is the phenomenon of reverse swing, that we make the flow turbulent on one side so that the boundary layer remains attached on the one side and keep it shiny on the other side, so that there could be a vacuum due to boundary layer separation. So that's why we could have a net force in the y direction, and the ball would move towards the shiny side, right? So that is the phenomenon of reverse swing, and then that is also, we can also explain the patches on the football ball. So we make it kind of patchy, made of patches, different patches, because we want it to be traveled more in space, but we cannot kind of put dimples on that because it would hurt the foot of the footballer. So we kind of make it in a big patches. So it also induces turbulence. So the discussion, all the discussions which I have done here, the crux of that is that if we want to reduce the drag force, total drag force, so we kind of put some kind of roughness on the sphere surface or solid surface, so that the wake region is less, and the total drag force would be less in case if there is surface roughness, right? But if consider we have got a streamline body. Yes, any question? Any question?
No, sir.
Okay. Okay, so now let's consider if we put dimple on a flow is happening from here. So if we put dimple on this flat plate and like kind of surface roughness, whether it would give us any advantage? No, because when we put roughness here, it would increase the friction drag. Friction drag would be more due to surface roughness. But because the pressure drag is already less in streamlined bodies, so that's why we don't put any surface roughness for the streamlined body, because the introduction of roughness element would always increase friction drag, but that friction drag increase in case of semi-fluid body would be very less as compared to reduction in pressure drag. So the overall effect of on the drag force would be substantial reduction if we put those dimples, right? But that those surface roughness is not advisable in case of flow over streamlined body, right? So I have explained these cases to you for the flow over cylinder. Now I am going to go through the slides which I have just explained. So the characteristic length of the circular cylinder, that is external diameter, as I have mentioned earlier, that the critical Reynolds number is 2 into 10 to the power 5. But as I have also explained that if we make it rough, then the critical Reynolds number can become 40,000, 50,000, depending upon the degree of roughness, right? So if you make it more and more rough, the flow would be turbulent in the boundary layer region more. So when the flow velocity is very low, which was the case in the figure A, we call it leaping flow, and in that case the flow would remain attached on the back hand side, and the predominant drag component would be friction drag when Reynolds number is less, and when Reynolds number is more, then the predominant or dominant component of drag would be coming from pressure drag. So both effects of which are pressure drag and friction drag are significant between 10 to 5,000. So it means that in between 10 and 5,000, though both. So let me write it here. When Reynolds number is less than 10, friction drag and friction drag and pressure drag. When Reynolds number is less than then friction drag would be more dominant, and there wouldn't be any pressure drag contribution, very less. When Reynolds number is something in the range of 10 to 5,000, then we would have both contribution from the friction. It means that both play part. But when we have got Reynolds number more than 5,000, then friction drag would be a very minor component of the total drag, and the 95% drag would be due to pressure drag. So it means that at higher velocity, we are more concerned about pressure drag in blunt bodies. In the streamlined bodies, for the streamlined bodies, we would have friction drag more. And for the blood bodies, we would have pressure drag. Okay. So that is the thing which is written here. And now I am going to show you the coefficient of drag graph with respect to Reynolds number. Now you can see the coefficient of drag, which is CD, which is drag force divided by half rho u square into area. That is shown for the cylinder as well as for the sphere. The solid line is for the sphere, and the dotted line is due to the CD value for the cylinder. right? Now you can see, and on the x-axis we have got Reynolds number, on the y-axis we have got coefficient of drag, right? So when the Reynolds number is 1 or up to 10, you can see a linear decrease in coefficient of drag value, right? So and in that coefficient of drag would be for the sphere, it would be 24 divided by Reynolds number. So it means that CD value is inversely proportional to Reynolds number. And so what does it mean actually? It means that the total drag force will reduce if we increase the Reynolds number. Is that the case? Does it make any sense that the total drag force will reduce if we increase the flow velocity? I think that it should increase. Sorry?
सारे नॉड नंबर के साथ ड्रैग फोर्स इंक्रीज नहीं करेगा?
बिल्कुल जी. Who are you? If you can tell me your name.
सर मोहम्मद उसामा.
As Muhammad Usama has rightly pointed out that it is counterintuitive that if we increase the velocity and we expect a decrease in drag force must increase with the decrease in Reynolds number. So it means that there is something we are missing. That missing part is I am going to explain it on the whiteboard. So because we are plotting CD value as a function of Reynolds number. So we are saying that CD is inversely proportional to Reynolds number when Reynolds number is less than 10, right? But if we write the formula of total drag force, that is CD into half rho U square into area, right? This is the formula. So if you remember, Reynolds number is equal to rho U d upon mu. This is the formula for the Reynolds. This is the formula, and then there is one thing you need to see here. It is a square. Here, if we say that CD is decreasing inversely proportional, so instead of U square, we can say that it is Reynolds number square. And here, instead of CD, we can write 1 upon Reynolds number. Is it clear to everyone? Because this is U square, so it means that we are talking about Reynolds number square. And here we have mentioned that CD is inversely proportional to 1 upon Reynolds number. So instead of CD, I have put Reynolds number. So this Reynolds number would be cancelled out with this square, and I can say that FD is proportional. FD is proportional to Reynolds number. So now, as I think Usama, it would be clear to you that as you were saying that with increase in Reynolds number, the total drag force would increase. So because instead of CD, we have put 1 upon Reynolds number. So, but because there is a velocity square, which is basically proportional to Reynolds number square, so 1 upon Reynolds number would be cancelled with this Reynolds number square, and that total drag force on the object would be directly proportional to linearly for Reynolds number when it is less than 10. Is that clear, Usama? And for that matter, everyone. Okay, so that is good because that is the most critical part that you understand this concept, that at low Reynolds number, total drag force would be directly proportional to the flow velocity. Now, if we move a little bit further, now you can see the mouse from 10 to power 3 to 10 to power 5. You can see kind of straight line here for the CD. So we can see that in the portion of 1,000 to 1 lakh, for both the cases, CD doesn't change very much. Is that the case? If I the portion here where I am trying to move the cursor, here the CD value is no more dependent upon Reynolds number. So in this formula, then again, if I write it for the range of FD is equal to CD into half rho U square into area. Now I am talking about Reynolds number which is greater than 10 to power 3, which is 1000, and less than 10 to power 5. So this is the range from 1000 to 1 lakh. In this, again, I would tell you that in this range, this CD line is almost a straight line for the sphere as well as for the cylinder. So we can say that CD is not a function of Reynolds number. So instead of CD, we can just put 1 here because it is no more dependent upon Reynolds number, so it is independent. CD is constant. So now this bit is Reynolds number square. So we can say that in this region, Ft is directly proportional to Reynolds number square. Here in the low Reynolds number, it was only proportional to Reynolds number linearly, but here it is proportional to Reynolds number square. What does it mean actually? It means that if at 10 to the power 3 the Reynolds number was total drag force was 2 Newton for a body. So if we increase it to 2000, it means that we have increased by twice. Reynolds number has been increased by twice. Uh, it it would increase like if we then it would increase by square. The drag force would be very high. It means that it would increase as the power of square. So it means that if we increase the Reynolds number from 1000 to 4000, so actual drag force was 2 Newton here. So at this maybe it would be kind of 4 square 60 Newton, right? 16 Newton. So it means that it would be very highly dependent upon Reynolds number. So it means that at higher Reynolds number, we need to make sure that the drag force is less. Okay, so and that functional form I have explained. Okay, after 10 to the power 5, you can see a sudden dip in this graph. So that is the point where the flow becomes laminar to turbulent, right? So because from laminar flow becomes laminar to turbulent, so as I have explained that the wave region becomes smaller because the flow separation occurs at theta is equal to 140 degree. So that's why we want that the ball would travel in this region so that it has got CD value very less. So that when CD value is very less, it would travel more distance in the space, right? So that is why we put dimples on the ball. So I hope that this point is clear to everyone. So this was it. So now all the things I have explained in detail that are written on the slide. So I will go it one by one. So for Reynolds number less than 1, there is a clipping flow and the drag coefficient decreases with increasing Reynolds number. For a sphere, it is 24 divided by Reynolds number. There is no flow separation in this region. So that's why friction drag will be more in this case and pressure drag would be less. Contribution of that. At about Reynolds number 10, separation starts. There would be standing vortices. Standing vortices I have shown you in figure B. And then at Reynolds number 15, there would be von Karman shedding, as I try to explain by running this animation. So that von Karman shedding at Reynolds number 15, it starts, and when we increase the Reynolds number, then it keeps on having more and more frequency of shedding of that more vortices would be shedded. So that is one thing. And then at Reynolds number 1000, the drag is predominantly due to pressure drag because there would be flow separation. In the region of 10,000 to 1 lakh, the drag coefficient remains relatively constant. As I have shown you, drag coefficient is constant. So here the drag force is function of Reynolds number squared rather than linear function of Reynolds number, which was 2 for the Reynolds number less than 10. And then this wave region for the turbulent case, you can see that the wave region is less. For the laminar region, laminar boundary layer, you can see the wave region is more. So it means that pressure difference force would be more for the laminar boundary layer, and it would this object would face more resistance when the flow is laminar. But for the turbulent case, it would kind of experiences less drag force. Pressure drag force, right? So I hope that all the things I have tried to explain it to you, you must have got the crux of it because I have repeated many times the same thing. So I hope. And then this is the CD graph as I have shown you for the circular cylinder here as a function of Reynolds number. Here it is shown for some other dimension. Like here, you can see for the flat plate when it is totally blunt body, there is no detection of CD. It means that we have got kind of if you see in the 10 to power 4 to 10 to power 6, you can say here this is a straight line. So straight line, and it would go on straight line because there is no flow attachment here. Concept of flow separation delay because the surface area available for the flow attachment is very small. So the I hope that you get this point that there wouldn't be any dip in the CD graph, as it was due to turbulent bond delay, as in the case of cylinder, right? Because the surface area available for the flow to be remain attached, that is this top surface and bottom surface for this flat plate, which is very small. So the flow would always be detached at this point, right? Always, whether that the flow is laminar or turbulent. And then this is the case for the circular cylinder, which I have explained in detail, that there is a dip because of the flow separation delay, because the flow becomes turbulent. And then if it is a spherical region, some kind of elliptical region, you can see that there is also a dip. And then we have got a streamline body. So for the streamline body, interestingly, that the because it is a decrease, CD is decreasing, so it means that even in the range of 10 to the power 3 to 10 to the power 5, that total drag force is only function of Reynolds number linearly, not Reynolds number square, which would be the case when this is kind of straight line. So that is the reason we want to make our vehicles or aeroplanes or something in a kind of a streamline body, so that drag force would increase linearly with the Reynolds number rather than to the square power of Reynolds number in case of semi-blunt bodies or blunt bodies. So I hope that this was of any. And then this table shows you the CD value for the flat plate. That is kind of the empirical correlation for different flow regimes for the transitional, turbulent, and then completely turbulent. And so that is given as a function of Reynolds number, and we need to conduct these experiments to get these CD coefficients for different flow regimes. So this was all about drag coefficient. Now we can take maybe 10 more minutes to discuss the other force, which is perpendicular to the flow direction. Drag force is always perpendicular to the flow direction. So the force which is created perpendicular to the flow direction, that is called lift force. So lift force, that is desirable in certain flow situations, like for the flow of some airborne vehicles like aeroplanes, missiles, rockets. So we need to have some kind of lift force so that they can travel in space against the gravity. So, but in many cases we don't want lift to be present. Like for the ground vehicles, we don't want to have more kind of lift force. Otherwise, there would be more jumps and there would be more wear and tear for the shocks which are placed to reduce that wear and tear. So that is the point. That is the reason we kind of slow down on the speed breaker, so that we don't have that kind of jumping of our vehicle, whether that is a bike or a car. So we want to reduce the speed. So lift is the point I was trying to make, that lift is desirable in certain conditions and undesirable in some other conditions, right? So before we okay, we will do this numerical maybe in next class, when we will finish the discussion of lift force as well. So lift is the, so we would do maybe in the next class. So before that, we would go through the theory of lift, and that force which is in the direction normal to the flow stream, right? So drag force is the that force which is perpendicular to the flow stream, and lift force is the force perpendicular. Some objects such as aerofoil are designed to generate lift. Other objects like vehicles are designed to reduce the lift generated to improve mobility and traction. So it means that we have got control of that object if it is remain bounded to the ground, stick to the ground, rather than it is jumping on the road. So that's where we kind of lose the control of the object. So these are the two things where we kind of one is desirable to generate lift, and one is undesirable thing. So now as we define the coefficient of drag, that was CD, that was equal to drag force divided by half flow unit scale into area. So similarly, we can also define CL, which is lift force divided by half flow unit scale upon area. Now this area, that depends where the lift is being generated, and I will explain it in the coming slide. So just hold on this area. I haven't specified the thing. For the CD, if we were talking about CD due to pressure drag, that was the frontal area, and when we talk about the CD due to friction drag, that was due to the surface area. So in this case, if we talk about this flow over this cylinder, then the frontal area would be this height into the depth into this bore. That would be the frontal area, and the surface area would be the circumference, which is pi dn, right? So that is the surface area. Okay, so for the lift, the surface area is important, that where the pressure forces are different. So lift on an object depends on the shape and orientation of body as well as relevance. When we talk about orientation of body, then we talk about a concept of angle of attack, right? So if this is kind of an aerofoil, it is not the best aerofoil, it is on. So try again. So if this is kind of aerofoil and the flow is coming from here, right? So this is excessive, we call it flow direction. And then there is a line which is called chord line. Here this is trailing edge. Trailing edge we call it when where the flow leaves that body downstream, and this is the leading edge. Leading edge is somewhere where the flow first come into contact with the body. So the points between leading edge and trailing edge, they can be joined by a line. We call it chord line. And this length is chord length. We denote it with C. Chord line we denote it with C. Chord line and chord length is denoted by C. And this angle, which is between the chord line and the flow direction, we call it angle of attack. So it means not the attack per se, but it means to say that how the flow is going to strike this object. So now you can easily see in this case, if the flow is coming here on the bottom surface, because it is striking more, so it means that we would have higher pressure here. So I can say that high pressure region here on the bottom surface, and on the here there would be some kind of flow separation. So here we would have lower pressure. So now you can see that if lower pressure is on the upper side and higher pressure is on the lower side, then there would be a net positive force in the y plus direction. It means in the upward direction, net upward force. So we call it net upward force, which is upward force. So that is why we kind of that aeroplane is kind of tilted so that the angle of attack is positive, and when we need to keep it to have the landing, then we would have negative angle of attack, so that on the upper side we have got higher pressure, and on the lower side we have got low pressure, so that it can come down. Okay, so that was one thing, angle of attack. So for objects operating in very low Reynolds number regime, the viscous effects are important, and the contribution of the shear stress to the lift may be as important as to the pressure. But at the cruise speed which we are talking about, then the pressure contribution is high. So for high Reynolds number flow, the effect of viscosity is negligible as compared to the effect of pressure. So here the flow is coming. This is the flow over a car. You can see that we have got stagnation pressure in front, then positive pressure on the windshield, but we would have negative pressure, low pressure on the upper side, right, and on the bottom surface as well. So we kind of try to make it such that it doesn't have positive lift, otherwise the traction of that vehicle would be less. So we want to make it more ground bounded rather than air bounded, because we want to have some kind of control of that car so that we can control it, right? So that is the pressure. The arrows going upward or away from the surface, that are showing that the pressure is less than the atmospheric pressure, and where the arrows are going towards the body, that is showing that the pressure is a kind of heavy, more than the atmospheric pressure. right? So we can see that the high pressure region on the front and on the windshield, and then low pressure region on the bonnet, on the roof, and at the rear end, and as well as at the bottom, right? So necessary condition to lift generate to generating lift, that is different pressure distribution on top and bottom surface. As I have explained, angle of attack, I have told you that it is represented by the way with the symbol alpha, angle at which the body is placed in the floor. So that is kind of this. If the flow is coming from this and chord length is this, then alpha is this. So it is kind of telling you that I have tilted this upward, but you can also kind of take it in the it is kind of uh, it is kind of not tilted here. So you can see that the chord length is aligned with the x-axis and the flow is coming from the downward side. So it means that the positive angle of attack, and then we can also have a non-symmetrical shape. Usually we have got non-symmetrical shape because we want to optimize this. That's why it's the just imagine that if the flow is coming from the positive zero angle of attack on this, what will happen? If it is coming from zero angle of attack, then the for the upper figure, then the pressure on the lower side would be equal to the pressure on the upper side. If we are talking about zero angle of attack, so it means that there wouldn't be any lift. But if we have got non-symmetrical aerofoil, then even if the flow is coming at zero angle of attack, the pressure on the lower side would always be greater than the pressure on the upper side, right? So that's why we would have positive lift force even for the zero angle of attack. So that's why we usually make non-symmetrical aerofoil shapes. So NECA aerofoils, they are usually non-symmetrical because they produce more lift, even at zero angle of attack and even at negative angle of attack. And the area I was talking about to create lift, that was the plane form area. That is the product of chord length and the this is the span which is represented with B here, and chord length is that is represented with C. So we can say it C into B, which is chord length into span of that wing. And this is the that aerofoil shape we talk about, that in the this is the shape we talk about, right? So lift force is perpendicular if the flow is coming from here. This is the leading edge, this is the trailing edge. Okay, and then aspect ratio, the ratio of the square of the wing length to the wing length is the B square, so we call it wing length, which is the span, and then divided by plane form area, which is the product of chord into length of that wing. So wing loading, that is a parameter which we define to characterize that how much lift is produced per unit area. So for Boeing 747, which is a commercial aeroplane, the wing loading is 7,200 Newton per meter square. So it means that for 1 meter square of wing plane form area, we would have 7,200 Newtons of lift force. But if we talk about, because this is very optimized value, but if we talk about the bumblebee, it has got only 48 Newton per meter square, but because it is very lighter in weight, so it can travel very easily. But for the commercial airplanes, we need to generate very high lift force per unit area. So that is defined by the wing loading. Okay, so then there is a condition of stall. That is very interesting area. That it means to say that here, if we increase the angle of attack very high, now the flow is coming from the right to left. So in the first figure, the angle of attack is not very high. But if we make it very high, it means that we make aeroplane vertical, then there would be a huge separation region at the back end. So lift would be very high, but because we are increasing the frontal area, when we increase the angle of attack, we are also increasing the frontal area. So what is the consequence of increasing the frontal area? Drag force would increase very high. So it means that if the drag force is very high, then the aircraft cruising speed wouldn't be maintained. And when the aircraft cruising speed wouldn't be maintained, then because the lift force is directly proportional to the speed of velocity, so the lift would eventually drop. lift, why? Because if we see the lift force relation with velocity, let me write it here. Lift force, which is FL, that is CL into half into rho u squared into area. Now, when we kind of increase the angle of attack by increasing, if we increase the angle of attack, which is alpha, we are increasing the FD value, which is uh, how it is increasing because the frontal area that is increasing. Now, because this drag force is increasing, it means that Reynolds number would decrease. When Reynolds number would decrease, then because here it is Reynolds number square, so lift force would decrease by a square. So it means that if the somehow the flow, the pilot mistakenly make it at very high angle of attack, then there would be a condition of stall, and then the plane would come down in a vertical direction, and that is not very ideal to have. So that is the flow separation region where we can see that huge flow separation. That lift force would be higher, but because the drag is very higher, so that's why Reynolds number would decrease and lift force eventually would decrease, and that airplane is going to crash. So that is not very ideal thing to have. And then there is one another thing that we use if you ever travel on a aeroplane. There are some kind of flaps on the trailing edge. So those flaps are used to create additional lift, right? So if I show you the figure for that, in this you can see some movable flaps on the trailing edge. So we can, if we make it more downwards, there would be more pressure on the lower side. It means that the lift force would be more. But the consequence of putting that flaps more and more in the downward direction, that the drag force would also increase. But it would also come with the increase in lift, which we usually employ in because it is only small portion on the trailing edge, so it would increase the CL value more as compared to CD. So here for the NECA profile, which is given, the number is 4012, I think. So you can see that it is CL upon CD, that is the thing we want to maximize, because we want to have maximum lift and minimum CD. So you can see that for this NECA profile, the optimal angle of attack is 4 degrees. So maybe less than 4, because at 4 degrees there would be a stall. So we want to keep it like between 0 and 2 for having maximum kind of output, because we don't want to have CL upon CD as maximum value, because it could be of no use if the aeroplane is going to crash, right? So, and then effect of that putting flaps, that is, let me write it on the whiteboard, that when we put the flaps in the trailing edge, so let me show it here. So it is kind of, this is a symmetrical aerofoil like this. Okay, so what we do that we kind of put some kind of joint, and we kind of put this. This is the flap, trailing edge flap. We call it flap. So what it does it do? That because it is when the flow is coming here, so because here would be higher pressure as compared to this portion, so it would have higher lift. So it would increase CL. But the second consequence, because it is perpendicular to the flow, so it means that CD would also increase a little bit, depending on this frontal area, right? So CL would also increase and CD would also increase. But CL increase is more because CD increase that can be overcome by putting more fuel. If we can spend more fuel, but lift would be generated more quickly in this case. So that effect is shown on this. On the left hand side, you can see the graph where we have put that wing flap at alpha 60 degrees. So you can see that even at 0 degree of attack, CL value is around 1.2, and if there is no wing flap, then the CL value is kind of near to 0 for this aeroplane. So there is a huge increase in CL value due to due to the incorporation of flap. So that is the 60 degree. What is 60 degree? That is the angle between the chord length and that flap. So this is at 30 degree. If we make it more downward, it would be 60 degree, and if we make it perpendicular, then it would be 90 degree. So this is the wing flap at 60 degree. Then, but on the right hand side, because as the saying goes that there is no freedom in this world. So because we are increasing the CL value, then it means that CD value would also increase. Now here the bottom three curves are the CD curve without that trailing edge flap, and this dotted line is the curve due to that wing flap and trailing edge flap. So you can see that CD value is also increased, but because we are not very concerned about that, because if we put more fuel, that CD thing we can control it more conveniently. So we usually use these flaps. So okay, these flaps, if we put it downward, it would increase lift, but if we put it in the upward direction, it would reduce lift. So we use these flaps when we in the upward direction when we want to land the aeroplane. But and when we want to kind of take off that aeroplane, that will kind of move them in the downward direction. So they are kind of movable by the pilot of the aircraft. So that is was the concept of wing flaps. So I hope that because these are the practical applications, so it would be of more interest. So if there is a